Okay, hopefully everyone can see my slides there. And the general topic is climate change. Here's a quick outline of what we're going to be talking about. Start with introduction and context, move on to discussion of the greenhouse effect, greenhouse gases, global consequences of climate change, local consequences right here in Monterey County, what needs to be done, global warming projections to the end of the century, some closing comments, and then finally we'll do question and answer. So we'll jump right in on introduction and context. I want to begin by showing you a graph of global mean surface temperature of the Earth, 5 million years in the past to the present. Now, global mean implies averaged over the entire face of the Earth. Surface temperature over the ocean means the sea surface temperature. Over the land, it's the temperature a couple of meters above the surface. And what you see here is, beginning with the Pleistocene epoch, about 2.5 million years ago, the Earth entered into ice age cycles. For the first 1.5 million years of the Pleistocene, the Earth was in a 40,000 year ice age cycle. And for the last million years, we've been in a 100,000 year ice age cycle. Now, I'm using the term ice age, that's the popular term, to represent these downward excursions of the temperature. Technically, these are called glacial periods, and the upward excursions are called interglacial periods, but I'm going to use the popular term ice age to describe these glacial periods. So why am I talking about the ice age cycle? We're here to talk about climate change. Why am I talking about ice age? Well, the human-induced climate change we are concerned with occurs against a backdrop of natural climate change. So we need to understand natural climate change and how the anthropogenic or human-produced climate change is different. And for the last couple of million years, the ice age cycle has dominated natural climate change. So the question is, do we understand the ice age cycle, or is it just some big mystery? And the answer is, we absolutely do understand the ice age cycle. In fact, the ice age cycle is driven by variations in the Earth's orbit around the sun and variations in the orientation of the Earth and space. That's what drives the ice age cycle. Now, I'm sure you all know that the Earth orbits the sun in an ellipse, such that in the summertime, the Earth is farther away from the sun than it is in the wintertime in the northern hemisphere. And that's good for those of us who live in the northern hemisphere because it makes our summers a little cooler, our winters a little bit warmer. But what you probably don't know, or you may not know, is this ellipse is not constant in time. It actually fluctuates, becomes more drawn out, more like an ellipse, less drawn out, more like a circle on a 100,000 year period, driven by the gravitational force of Jupiter and Saturn acting on the Earth. Now, this picture is exaggerated here. It's not nearly this large, but nevertheless, it's enough to have a profound impact on climate. Now, I'm sure you also know that the Earth's axis of rotation is inclined relative to the plane in which the Earth orbits. That's, of course, what gives us the seasons. In Northern Hemisphere summer, the North Pole is tilted toward the sun, and Northern Hemisphere winter, it's tilted away from the sun. But what you may not know is this tilt is not constant in time. It rocks back and forth between about 24.5 degrees to 22.5 degrees on a 41,000 year period. And that's driven by the gravitational force of the sun and moon acting on the Earth. And finally, I'm sure you know that the North Pole points to the North Star, which in fact is Polaris. What you may not know is that the Earth wobbles on a 27,000 year period, such that 13.5 thousand years from now, Vega will be the North Star, and then 13.5 thousand years later, then it'll have wobbled back to Polaris being the North Star. So how does this drive the ice age cycle? Well, it works like this. When these orbital variations or this orbital forcing comes into phase, or you can think conspires to decrease solar radiation striking the Earth during the northern hemisphere summer, that drives us into an ice age cycle. Now, there are three amplifying feedbacks that are important here. Without these feedback effects, this orbital forcing actually wouldn't be strong enough to drive the ice age cycle nearly the way it is. But there are three feedback effects that come into play. The first is called snow ice feedback, and it works like this. With decreasing global temperatures driven by these orbital variations yields increasing snow and ice, and that reflects more sunlight back out to space, which decreases the sunlight absorbed by land and sea. That further decreases the temperature, and you keep going around this feedback loop, and it amplifies the cooling. Similarly, we have the water vapor feedback loop. With decreasing global temperatures, that yields decreasing evaporation of water from oceans and land. That produces decreasing water vapor in the atmosphere. Water vapor is a greenhouse gas which traps outgoing radiation. That further decreases the global temperatures. And again, you go around this feedback loop. And then finally, there's the CO2 feedback loop. Decreasing global temperatures yields decreasing release of CO2 from the oceans and the biosphere. That produces decreasing CO2 in the atmosphere, which further decreases global temperatures since CO2 is an important greenhouse gas. So that produces this transition to an ice age. And then when you come out of the ice age, it works the opposite way around. When the orbital variations produce increasing solar radiation striking the Earth during northern hemisphere summer, you go around the feedback loops in the opposite direction of positive feedback loops that work both ways, and that produces a recovery from the ice age. Now, why do I keep talking about northern hemisphere summer? Well, there's an important asymmetry in the world, and that is in the northern hemisphere, there's a lot more land, so there's a lot more snow on the ground. And also at the North Pole, we have an ocean, the Arctic Ocean. And the ocean is very, very strong in producing the snow ice feedback effect, because when the sea ice melts in the Arctic, it leaves behind very dark ocean, which absorbs a lot of solar radiation. So basically, the snow ice feedback effect works most strongly in the northern hemisphere, and that's why the northern hemisphere summer is the key thing here. So that's how the ice age works. And back to the 5 million year view here. And now I'm going to zoom in way over here and take a look at the very tail end of the last ice age. We're going to be looking back 22,000 years, and it looks like this. We're looking at the same parameter as before, global mean surface temperature of the Earth, but now over the past 22,000 years. And a couple of things here. This is basically the last ice age right here. This is the approximate beginning of human civilization. This warm period here is called the Holocene interglacial period, and human civilization began right about here, about 9,000 years in the past. This is the recovery from the ice age driven by eccentricity cycle, which we just learned about. So the Earth's orbit was becoming less like an ellipse and more like a circle, and that was producing this warming effect here. This cooling trend, which has been happening about the last 7,000 years or so, is driven by the obliquity cycle we just learned. So what's happening here is the Earth has been losing tilt. It's lost about 7/10 of a degree of angular tilt, and that's led to this long-term cooling trend. There are other things that are visible here. This 1,500-year period of interruption of the ice age recovery is called the Younger Dryas period. This little bump here is called the medieval warm period, and this little dip right here is called the Little Ice Age. And then finally, we come to this red spike. This red spike here is in fact a post-industrial global warming that we are concerned with. So there are two things that are immediately apparent about this red spike. First of all, it's going in the wrong direction. It should be cooling. We should be cooling. We were cooling until all of a sudden in the industrial age, we started warming very rapidly. And very rapidly is the key words here. In fact, we're warming about 20 times faster than natural climate change. This is what natural climate change looks like. This is 20 times faster in the wrong direction, not natural climate change. So what we've been seeing for the past 100 years, we've been warming about 20 times faster and in the opposite direction of natural climate change. And that's how we know this is absolutely not natural climate change we've been experiencing for the past 120 years or so. I'm going to zoom in once again. Now we're looking at, again, the same parameter, global mean surface temperature of the Earth, but now going back to 1850. So this is a plot from 1850 to 2017 from 5 different sources here, 5 different approaches to data. I won't go into detail about each one, but basically all of them involve in situ surface data. That would be data taken by ships measuring the sea surface temperature. That would be data taken by weather stations over land. Others also include upper air data. That would be weather balloon data, even satellite data. Some of them involve sophisticated numerical weather prediction models running what are called data assimilation cycles, very sophisticated statistical techniques. Others are much simpler. But the point is, these 5 different approaches to using the data from 5 different groups all paint the same picture. And the picture is as follows. From 1850 to 1880, not much of a change. From 1880 to 1910, slight decline. From 1910 to 1945, a pretty strong upward trend. 1945 to 1975, slight downward trend. And then beginning in the mid-80s, a very strong upward long-term trend, such that we are now running about 1.2 degrees centigrade above the pre-industrial level for global mean surface temperature of the Earth. Note that the temperature doesn't go up in a straight line. There are all these zigs and zags here. It's kind of like the stock market. It's like volatility in the stock market. Stock market doesn't go in a straight line. The long-term trend is upward, but that doesn't imply it's upward every day or every year. That's what's kind of what's going on here. So what's driving that? Well, to understand that, we need to understand the fundamental differences between weather, climate variability, and climate change. And the thing that differentiates these three classes of phenomena in the atmosphere is, in fact, increasing time scale and space scale. So what's that? Well, time scale is just a fancy way of saying the lifetime of phenomenon, and space scale is just a fancy way of saying the size of the phenomenon or its domain of influence on the face of the Earth. So we see down here in the far left, on time scales running from minutes to months, we have weather. In the middle zone, running from months to decades, we have climate variability. Climate variability we're actually pretty familiar with. We're all familiar with weather. Climate variability we're also familiar with. It's El Nino, for example. ENSO here is called the El Nino Southern Oscillation. That includes El Nino and its twin La Nina. There's also the Pacific Decadal Oscillation here, the PDO, the Atlantic Multi-Decadal Oscillation. These yield warm years and cold years, wet years and dry years, that kind of variability. But it happens on timescales of months to decades, on space scales of about the size of the Pacific Ocean. And then finally, to the far right, we have climate change.
I'm getting a presentation on climate change.
Again?
Yeah, it's on our Monday morning group thing. So
yeah.
Okay. So let me try to reach you at the end.
Yeah.
Okay.
Yeah, Peter, if you could mute your microphone, please. And the far right, we have climate change, which extends from decades to centuries, even to millennia, and it's a global phenomenon. Now, these classes of phenomena actually do overlap a bit. That's why I've drawn the arrows overlapping here. But the point is, those zigs and zags we were just looking at, these zigs and zags here, that's climate variability. That's things like El Nino and La Nina. It's not climate change. A really good rule of thumb I'd like you to remember and take away is if you're looking at a trend and wanted to do something about climate change from that trend, it needs to be a record that's 30 years or longer. If you're looking at a record that's 20 years or less, you're not looking at climate change, you're looking at climate variability. 20 years to 30 years, that's kind of gray area, but you really like to be closer to the 30-year trend. In fact, if you're looking at a 50-year trend, it's even better. Now, I'm going to show an animation of one of these products. In fact, it's going to be the NASA product. It's going to be a global animation. Pay particular attention to what happens in the 70s. That's where this big upward trend occurred here. And what we're going to be looking at is going to be an animation of temperature anomalies. Now, temperature anomaly is just a fancy way of saying temperature difference from a reference field. And the reference field that's going to be shown in this, or used in this case, is the 30-year average surface temperature from 1951 to 1980. Now, a couple of things about this data. First of all, it's a lot of data. Over the land, it's a couple billion observations. Over the ocean, it's about 350 million observations. No computer models here. If you're worried about computer models, forget it. They're not here. No satellite data here. There are problems with satellite data in dealing with climate. No satellite data here. This is simply surface in situ data. You may be aware of the urban heat island effect, the real effect whereby all the heat trapped by the concrete and buildings and so forth and cities can produce anomalously warm temperatures. Forget it. That's not here. There's a couple hundred stations that were emitted from this analysis they were deemed to be contaminated by urban heat island effect. If you're a real aficionado of this business, you may be aware that in the first half of the 20th century, sea surface temperatures were measured by ships using bucket temperatures. They actually threw a bucket over the side and attached to a rope, pulled it back up, stuck a thermometer in. Transitioning in the second half of the 20th century, there was a transition to doing away with bucket temperatures and moving toward engine injection temperatures. That's the cooling injection of seawater to cool the engines, and a thermometer is put in that system to measure temperature. Well, there's a bias between those two ways of measuring temperature. The bucket temperatures were biased cold by about 1/10 of a degree centigrade, and the injection temperatures were biased warm 1/10 or 2 of a degree centigrade. That's all been corrected out. Don't worry about that. That data has been carefully corrected out. So I'm going to roll this animation. And I'm going to call out the decades. You keep focused on the patterns as they're changing. I'll call out the decades. Pay particular attention to the 1970s. And again, the oranges are warm. Dark orange is 2 degrees centigrade. Dark blue is minus 2 degrees centigrade. So here we go. Okay, we're in the 1880s, 1890s, 1900s, 1910s, 1920s, 1930s, 1940s, 1950s, 1960s, 1970s, 1980s, 1990s, 2000s, 2010s, and we end up at 2018. So a couple things from this. First of all, the land is warming faster than the sea, but the sea is definitely warming. You see all these yellows here. As far as the land is concerned, the farther you go north towards the Arctic, the more the warming is occurring. The warming is greatest as you go more towards the poles, which is not a great thing because that's melting the Arctic ice, of course. It's not warming everywhere. Notice there's a blue patch here. This is associated with changes in the Gulf Stream circulation. There are some blue patches along the Antarctic. So it's not warming everywhere. When you talk about global warming, you really need to talk about the global record. If you put your thermometer here, then you're going to find it's cooling, it's not warming. And finally, if you look at the continental United States, notice that the western 25% or so of the country is warming quite a bit more than the eastern 2/3. Particularly where we live in the West, it's been warming, and with that warming, of course, has come drying. So what's going on here? Well, in fact, it is the greenhouse effect. And to understand the greenhouse effect, you really need to first look at the Earth's annual mean energy budget. Here's a depiction of that. This is an average over a 6-year period from 2000 to 2005. So these are flows of energy into the Earth, in and out of the Earth. Averaged day and night over every day of the year, actually over a 6-year period, over the average of the entire face of the Earth. And this is what it's all about. Basically the flows of incoming and outgoing radiation, and then it gets transformed and transferred in the ways that are depicted here. Now you may ask, what about other sources of heat? For example, what about heat from the center of the Earth? That's, for example, how geothermal energy works. Heat is coming up from the center of the Earth. Well, it's really small. It's about 25 times smaller than the current radiative forcing of the Earth. What about heat from factories, buildings, transportation, et cetera, waste heat from buildings? Even smaller, about 77 times smaller. Tidal friction, 330 times smaller. Any other source of heat you can think of is trivially small compared to what's depicted on this chart. This really is the ball game, what's depicted here. So with that background, the greenhouse effect works like this. The Earth is warmed by incoming solar radiation, in fact, about 340 watts per square meter on average. And it's cooled in 2 ways, by reflected solar radiation and outgoing long-wave radiation. So long-wave radiation is the infrared radiation that the Earth radiates back out to space in an attempt to cool itself down. And the outgoing long-wave radiation is trapped by greenhouse gases and thus warm the lower atmosphere and the surface of the Earth. And then finally, human activities increase greenhouse gases in the atmosphere and increase the warming. Now, here are the greenhouse gases. These are the so-called long-lived greenhouse gases, the ones that are most important. The top of the list is water vapor. More outgoing infrared radiation is trapped by water vapor, which of course we perceive as humidity in the atmosphere, than any other gas. But note that I've colored it differently from the others, so I'll come back to that in a minute. Next down the list is CO2, carbon dioxide, methane. The F gases are fluorinated gases. These are man-made gases that are used in coolants, for example, in refrigerants, also used as certain solvents, electrical insulators, and finally, nitrous oxide. Water vapor is different because water vapor is in balance with the natural hydrologic cycle, and humans are not putting large amounts of water vapor into the atmosphere. Now, the water vapor in the atmosphere is increasing as the hydrologic cycle is being nudged towards warmer temperatures with the ocean warming more. But generally speaking, water vapor in the atmosphere is not going up um, because it's dramatically because it's in balance with the natural hydrologic cycle. So as a result, it's not a driver of global warming. It's important to understand that. It does participate in global warming through that water vapor feedback effect we talked about briefly with regard to the ice age cycle. So as the Earth is warming, there's more evaporation from the oceans and more water vapor in the atmosphere, but it's not driving global warming. These other gases that I've colored in magenta, they are driving global warming because they are not in balance with any natural cycle. They are being put in the atmosphere in large amounts by humans, and they are increasing very steadily and very rapidly in the atmosphere. Now, this is not just me talking. There's in fact an overwhelming international scientific consensus on this matter, just along the lines of what I've described to you. And this is just a partial list of leading science organizations all around the world who have endorsed what I've been saying. That includes the National Academy of Sciences, the U.S. National Research Council, American Association of Advanced. You could go down the list, and all the most prestigious organizations in the world do confirm human-induced global warming. In fact, there is an overwhelming international scientific consensus on the following 3 points. Number one, over the past 120 years, the Earth has been warming and the climate has been changing at alarming rates. Number two, this global warming and climate change has been driven almost exclusively by the accumulation of greenhouse gases in the atmosphere caused by human activities. And finally, without dramatic reduction in the emission of greenhouse gases into the atmosphere, the Earth will continue to warm and the climate will continue to change to the detriment of humankind. So stated succinctly, point one, it's happening. Point two, humans are causing it. And point three, it's not a good thing. So let's talk about these greenhouse gases. These are, again, the long-lived greenhouse gases. And what we're looking at here is the percent contribution to the current rate of global warming. And you can see the dominant greenhouse gas is carbon dioxide. Not saying the others aren't important, we don't have to worry about them, we do. But in fact, carbon dioxide is really the dominant driver of global warming. So here's a look at CO2 in the atmosphere from 1700 to 2019. And what you can see is that prior to the Industrial Revolution, CO2 in the atmosphere was averaging about 280 parts per million. And beginning with the Industrial Revolution, particularly ramping up in the 1960s, we've now increased to about 415 parts per million, which is an increase of almost 50% over the pre-industrial level. Another way of looking at it is the amount of mass in the atmosphere. Since from 1850 to 2018, the total amount of CO2 emitted by human activities amounted to about 2 trillion tons, not billion, trillion, 2 trillion tons. And this increased the CO2 in the atmosphere by about 1.1 trillion tons above the pre-industrial level. And we are currently putting CO2 into the atmosphere at about 40 billion tons per year. So where is it coming from? Well, the number one source of CO2 is China by a pretty wide margin. We're number two right here. China and the US together account for more than 40% of CO2 emissions. Then comes India, Russia, Japan, Germany, and down on the list. Another way of looking at it is per capita CO2 emissions. Well, there's a lot of people in China, so they drop pretty far down the list here. Their per capita emissions are about 7.5 tons of CO2 per year per person. But the US is number one, 16.5, or the average American puts 16.5 tons of CO2 into the atmosphere per year. Australia and Canada are pretty close behind us though, 15.4 and 15.1. California is doing quite well. Good news story for California. Although the average for the US is 16.5 tons per person, the average for California is only about 9.2 tons. So we're doing, I think we're either the best in the country or pretty close to being the best in the country in terms of low per capita emissions. Now I want to introduce two terms here you may come across before we go much further. The first is called global warming potential. And usually it's usually presented as GWP sub 100. That means global warming potential over a 100-year period. Global warming potential takes into account two things: the potency of the greenhouse gas and the lifetime of the greenhouse gas in the atmosphere. Carbon dioxide is arbitrarily a given value of 1, so everything is referenced relative to carbon dioxide. So you scale for both the potency of the gas and the lifetime of the gas. So for example, methane, also known as natural gas, on a potency, molecule by molecule basis is about 280 times more potent than carbon dioxide, but it only stays in the atmosphere about a tenth of the time. The nominal residency time for CO2 in the atmosphere is 100 years. The nominal residency time for methane in the atmosphere is only 10 years. So you got to divide by a factor of 10, and you come up with a global warming potential of 28. Do the same thing for nitrous oxide. It's 265. But look at these fluorinated gases. Fortunately, there's not much fluorinated gases in the atmosphere right now, but they have huge global warming potential. They're very potent, and they persist for thousands or actually tens of thousands of years. So we really need to keep these fluorinated gases out of the atmosphere because they have a tremendously powerful global warming potential over a 100-year period. Now, there's another term you may come across, which is CO2 equivalent. It's often written like this, CO2e. And to get that, all you do is you just multiply the amount of greenhouse gas emitted in tons times its global warming potential. So for example, if you have an operation that's producing 1 million tons of methane into the atmosphere every year, that's the equivalent of emitting 28 million tons of CO2 emission into the atmosphere every year, because you're basically just taking that 1 million and multiplying times the global warming potential of methane, which is 28, you come up with 28 million tons. So with that background, let's take a look at US greenhouse gas emissions in 2018. And what we see here is that CO2 is definitely dominant. 81% of all CO2 emissions or 81% of greenhouse gas emissions, when you take into account global warming potential, is in fact CO2, followed by methane, nitrous oxide, and fortunately the fluorinated gases are way down here. Now, the vast majority of US CO2 emissions are coming from these three sectors. Transportation, 27%, 28%. Electricity generation, this is basically energizing the electric grid. And finally, industry, mainly cement and steel production. The other greenhouse gases are coming from these other sectors: agriculture, commercial buildings, and residential buildings. So what are the global consequences of all these greenhouse gases going in the atmosphere and in this climate change? Well, I'm not going to read off all of these. I'm just going to hit the high points. I am going to share my slides. So if you don't have time to read everything here, don't worry about it. You can come back and look at it later. Just going to hit the high points. Increasing frequency and intensity of severe storms, increasing frequency of life-threatening heat waves, increasing frequency and intensity of floods in wet regions, increasing frequency of droughts and wildfires in drier regions like where we live, decreasing mountain snowpacks and earlier snow melt, rising sea levels, increasing mortality of coral reefs, that's called coral bleaching, decreasing productivity of fisheries, and loss of biodiversity. I want to highlight a couple of these, and the first is going to be the weather aspect. Here's to understand what's going on with global warming and weather, we need to take a look at the vertical structure of the atmosphere, and it's depicted here. These are the different layers of the atmosphere: troposphere, stratosphere, mesosphere, thermosphere, up to basically the edge of space. All the weather we experience occurs down here in the troposphere. And to put that in perspective, when you're flying in a jet airliner, you're kind of near the top of the troposphere here. And when the pilot says we're going to try to climb above this weather, you're going up to the lower part of the stratosphere. The point here is that the warming of the atmosphere due to global warming is happening way down here in the lower half of the troposphere. It's warming down here, but it's cooling everywhere above. And so what that's doing is it's destabilizing the atmosphere. It's cooling above because the heat that would normally warm the atmosphere above is being trapped down here. So you're heating the atmosphere from below, cooling it from above. That's making the atmosphere more unstable because warm air rises. And when warm air rises into cool air, that produces the kinetic energy of storms. So we're making the atmosphere more unstable by heating it from below, cooling it from above, and you're also making the atmosphere more humid as the ocean is warming and there's more evaporation. And as a result, that also makes the atmosphere more unstable because when that moisture condenses into clouds, into precipitation, that releases heat, which further drives vertical motions and convection and instability. So these changes are increasingly fueling strong storms and severe weather. And indeed, when you look at the long-term trend of severe weather, severe storms, severe floods, heat waves, droughts, and wildfires, you see there is a clear upward trend over the past 30 years. Now, this is not damage, or it doesn't take into account, inflation and things like that. This is just purely counting the number of storms, and you can see there's been a clear upward trend in severe weather. The other issue is sea level rise. What we're looking at here is observed sea level rise, global sea level rise from 1900 to 2015. The part in blue here is from tide gauge data. The part here in green and red here is from satellite altimetry data. And you can see from 1900 to 2015, global sea level has gone up about 8 inches. But the disturbing thing here is you can see it's accelerating, and we expect it to continue to accelerate. We're on track right now for a rise of about 1 meter of global sea level between now and the end of this century. But it could be much higher. It could be as high as 2 meters. There's a lot of uncertainty in sea level rise, and we'll talk about a little bit more about that later. What about human consequences? Well, again, I'm just going to hit the high points here. Increasing economic costs, increasing competition among nations for water and food, increasing displacements of people and unrest in populations susceptible to recruitment by violent extremist groups, increasing threats to human health, and finally, increasing human mortality from heat waves, severe weather events, starvation, disease, and war. Not a pretty picture. What about local consequences right here in Monterey County? Well, the state of California has been funding about every other year studies, climate assessment reports. And the fourth climate change assessment report, which came out a couple years ago, was really focused on looking ahead where we're going. It's basically a modeling study using the model ensemble from the IPCC, the Intergovernmental Panel on Climate Change. And I won't go into great details about that study, but I'm going to summarize the results they found and what they're predicting for Monterey County. And again, I'm not going to read all the details here, but just hit the high points. So for the business as usual scenario, and I'll just mention about that, there's, when you're trying to predict how things are going to be in the future, you have to make some assumptions about what are the CO2, what are the greenhouse gas emissions going into the future. And there are, 3 or 4 different scenarios that the IPCC has defined. The most extreme case is called business as usual. It's also sometimes referred to as RCP 8.5, which is representative concentration pathway 8.5. And business as usual means we just give up. We throw up our hands and just, don't try to do anything. And so that's kind of the upper bound. We know we're going to do better than that. We are doing better than that. But the business as usual scenario provides a useful upper bound, and it also helps reveal trends. So the study that I referred to, or these results I'm presenting, are for the business as usual kind of upper bound case. So what we have will be increasing temperatures. And by 2100, in this worst case scenario, about 7 degrees Fahrenheit above current levels in Monterey County. More frequent and severe storms in the winter. Increasingly drier conditions heading into the summer dry seasons and the fall fire seasons. And finally, increasing prevalence of local wildfires and smoke from distant wildfires. The kind of trends we've been seeing for the last 20 years or so, they're going to continue, and they're just going to get worse. Increasing likelihood of severe and extreme droughts, with happening about twice as often. So droughts we would experience about once every 20 years. We would expect to happen once every 10 years. Droughts we would expect to happen every 50 years, would happen about every 25 years, that kind of thing. Decreasing snowpack in the Sierras and less statewide resilience to drought. And finally, rising sea levels and more frequent and severe winter storms threatening oceanfront properties, particularly after 2050. Here's what, again, for the business as usual, most extreme case, here's what sea level rise is predicted for in Monterey County. The upper row here is in centimeters, the lower row is in inches. And a lot of uncertainty. You can see, first of all, things really take off after 2050. The sea level rise is pretty modest up until about 2050, but it really accelerates after that. That's because that's when we expect the Antarctic ice sheets to start melting much more rapidly than they are now. But there's a lot of uncertainty. Could be as high as 94.5 inches, as low as 28.3 inches. But the most likely value is here around 54 inches, and that's pretty significant. That's like, that's over 4 feet.
Jesus.
So what needs to be done to address this problem? I'm a big fan of Project Drawdown, and I refer you to their website, drawdown.org. Project Drawdown is a nonprofit organization that proposes, analyzes, and ranks solutions for reducing greenhouse gases in the atmosphere, with the goal of reaching drawdown, the point at which time concentration of the gases come down on a year-to-year basis. It was founded in 2014 by noted environmentalist Paul Hawken. They present 80 solutions for reducing and sequestering carbon dioxide oil in the atmosphere. These solutions consist of technologies, practices, and policies organized into 9 sectors and implemented in 2 scenarios. Essentially, it's a roadmap for stopping and eventually reversing global warming and climate change. There's a book out called Drawdown, which was a New York Times bestseller, but they've also come out with a brand new report just last year. It's called Drawdown 2020 Review, which they basically updated everything, and that's what I'm presenting here. They organize their solutions into 9 sectors: electricity, food, agriculture, and land use, industry, transportation, buildings, health and education. A lot of this has to do with trying to limit population growth around the world. Land sinks, coastal and ocean sinks, and engineered sinks. So I'm just going to quickly give you a flavor of these. In terms of electricity, here are a partial list of their solutions. Some will be familiar to you, others maybe not so. Just want to give you a flavor for them. LED lighting, wind turbines, hydropower, nuclear power, utility storage, microgrids. On nuclear power, Drawdown sees nuclear power as an important part of the mix between now and the rest of this into the century, but they're not advocating nuclear power as a long-term solution. There are a lot of problems with nuclear power, and so it's an interim solution, but not necessarily a long-term solution. Transportation, carpooling, public transit, high-speed rail, electric cars and trains, new forms of aviation. Someday you're going to be getting on an airplane that's powered by electricity. It's an electric airplane, and it's going to fly you from Monterey to San Francisco, Monterey to Los Angeles. Your commuter flights will be electric-driven powered planes. That's probably going to happen in about 20 years. Are you ever going to get an electric plane that's going to fly you to London from San Francisco? No, that's never going to happen. But you are someday going to, or people are someday. It's going to probably be a long time away, probably the latter part of this century. But at some point, we're going to have airliners, wide-body plane jets that look a lot like the planes we have now, that are going to be powered by liquid hydrogen. And those planes are going to fly from San Francisco to London with a 0 carbon footprint. That's definitely going to be happening at some point. Food, agriculture, and land use. New ways of doing agriculture, conservation agriculture, regenerative cropping. Reducing food waste is a big part of it. The world throws away about 1/3 of the food we produce, and food production has a big carbon footprint. Industry, looking for different ways, different materials to take the place of cement. Cement intrinsically produces a lot of CO2 into the atmosphere. Recycling, refrigerant management is the way of keeping these fluorinated gases I talked about out of the atmosphere. Landfill methane capture is very important. Making buildings better, more efficient. Building automation systems, insulation, dynamic glass, all these kinds of things. Net zero buildings are the big thing coming along. Use of heat pumps, district heating in cities, all those kinds of things. Land sinks, got to take care of our forest, particularly temperate and tropical forest. Manage grazing to take care of the grasslands. restoring abandoned farmlands, bamboo production, tree plantations on degraded land, all those kinds of things. So what's it cost? It doesn't happen by itself. There's some costs associated with this. And one really good thing about Drawdown, they've done a great job of costing out these different solutions. And they do it in two scenarios. The first scenario is hold global warming at 2 degrees centigrade above pre-industrial. That's sort of the guardrail scenario for the Paris Climate Accord. The Paris Accord said we need to hold warming to below 2 degrees centigrade. That's what we really need to do to prevent a lot of bad things from happening. But we really like to go to 1.5 degrees. We really like to hold it to 1.5. So this is the most stringent recommendation of Paris. This is kind of the guardrail recommendation of Paris. And Drawdown is price it out both ways. In terms of the most aggressive target, 1.5, the global cost would be, the 30-year average annual global cost would be $1 trillion a year. So $30 trillion over, over the next 3 years is what would be required to get there. But the good news is there's a return on investment. In fact, investing $1 trillion a year on average, you would get a return on investment of about 4.8 trillion. Now, if you apportion these costs out according to GDP, the U.S. bill would be about 250 billion a year over the next 30 years, but on average would save about 1 trillion a year over the next 30 years. And for point of reference, I'll note that just last week, President Biden asked Congress for 500 billion per year for the next 4 years, basically $2 trillion to deal with climate change, which is twice this target value here. So the Biden administration has been trying to get off to a very aggressive very aggressive start in dealing with this issue. I'll also point out that according to the International Monetary Fund, the fossil fuel industry is subsidized at about 5.2 trillion per year globally. And in the US, according to the IMF, the fossil fuel industry is subsidized at 650 billion per year. So you could reduce, only by a factor of 2 this subsidy, and you'd have plenty enough money to address this issue. So it's not like this is out of reach. It's definitely a doable thing. So where are we going? What are the projections to the end of the century? Here's this picture we looked at before, the 22,000 year look, beginning of human civilization right here. Here's where we are right here. If we adopt the most stringent recommendations of the Paris Accord, if we invest in the world at $1 trillion a year for the next 30 years, we would hold global warming to right about here, 1.5 degrees above the pre-industrial level. If we adopt, on the other hand, that business as usual scenario, which is the worst case scenario, which we throw up our hands and don't do anything, then we're going way up here, 4.5 degrees. See, now look how extreme that is. That's about the difference between an ice age and not an ice age. That's incredibly extreme. That would be catastrophic because it would kick other feedback loops would kick into play here, and that would be a total disaster. Here's where we're going on track for right now. And this is very recent. Just last month, the UN released its annual report card on how well the world is doing in meeting the Paris goals. The world is way behind, and as a result, we are currently on track for 3 degrees above pre-industrial warming by the end of this century. Here's where I personally think we're going to end up. This is my prediction. And others are going to disagree. Others will probably say we'll do better. Others will probably say we'll do worse. But my reading of the tea leaves is we're going to end up right about here, about 2.5 degrees C above pre-industrial. Part of what's driving my little bit of optimism here is the fact that the U.S. of course, has rejoined the Paris Accord and is now showing a lot of leadership, and the world is taking note. And as a result, I think we can do much better. For the past 4 years, we've been out of the accord, and the other countries have looked at us and said, well, if they're not going to play, we're not going to play either. But now we're back. And in fact, the Biden administration is seeking a very significant investment over the next 4 years. So I think we'll do better than 3. I think we'll end up down here around 2.5 degrees. Now, that's bad enough because at 2.5 degrees of warming, we're going to have a lot of severe weather. We're going to have hurricanes that are going to make the current Cat 4, Cat 5 hurricanes look pretty mild. We're going to have superstorms that are going to make Superstorm Sandy look mild. We're going to have lots of issues of dealing with drought here in the West. So And that's pretty bad. You know, it's going to be tough to handle that, but that's pretty much, I think, where we're going. So I'm going to now call on the greatest naturalist of our time, David Attenborough, to make some closing comments along with a few other people. And then we'll open it up to question and answer. Here we go.
Standing here in the English countryside, it may not seem obvious, but we are facing a man-made disaster on a global scale. In the 20 years since I first started talking about the impact of climate change on our world, conditions have changed far faster than I ever imagined.
Before we started to burn coal, the amount of carbon dioxide in the atmosphere was about 280 parts per million. It's now over 400 parts per million. And the planet gets warmer and warmer.
We are seeing the impacts of climate change now play out in real time. They're no longer subtle.
We're not just talking about an inconvenience. We're talking about people's lives, their livelihoods, and their communities being damaged.
Join the dots. It's happening. It's happening in your world. It's happening in my world. And let's be very clear about this. It is going to get much worse.
It may sound frightening, but the scientific evidence is that if we have not taken dramatic action within the next decade, we could face irreversible damage to the natural world and the collapse of our societies.
There are thousands of scientists around the world in almost every single country working to understand what will happen in the future if we don't act, we don't do more. They predict that if we carry on as we are now, where CO2 continues to increase, we would hit 1.5 degrees global warming by between 2040 and 2050.
We're on course to go through 1.5 degrees in just a few decades' time, and the models differ slightly as to exactly when. And not long after that, we're on a trajectory to go through 2 degrees.
It really becomes difficult to see at such levels of warming how we're going to maintain our agriculture such that the population of the world can actually feed itself.
And ensuring people have access to clean, safe drinking water will become much more difficult.
Developing countries are at the front line of this battle.
Those parts of the globe which will suffer the most and the soonest are not those parts of the globe which have actually loaded all those carbon dioxides in the atmosphere in the first instance.
But you have to understand this is also a crisis for the world. The fact is that if the poor are suffering today, then the rich will also suffer tomorrow.
We're running out of time, but there is still hope.
It's actually not that complicated. We need to shift our energy system away from fossil fuels that produce greenhouse gases and towards renewable energies that don't.
We still have time to turn everything around, to pull the emergency brake and to take action. But that short period of time isn't going to last for long.
There's a message for all of us in the voices of these young people. It is, after all, their generation who will inherit this dangerous legacy. We now stand at a unique point in our planet's history, one where we must all share responsibility both for our present well-being and for the future of life on Earth.